Guys, so I'm back with part 2 and we're starting on supermodels on page 30. So remember, models are representations of things that scientists can't control. Either they're too big or too expensive, or they are uncontrollable, like the weather. So how does a bat fly? How might Saturn's rings look close up? How does a heart work? So these are some science questions that can be answered with models, right? You guys know also that you can use models for weather. That's how they predict certain weather trends, and the planets we certainly can't control. So they use models for to see ask to answer questions about those types of things. So when modeling is needed, when scientists can't experiment with the real thing, they use models, and it helps them understand systems that have many hidden parts, such as an ant colony or the internet. Scientists draw conclusions and make predictions by studying their models. The closer the model represents the real thing, the more useful it is, which makes sense. So scientists change their models as they learn more. That makes sense as well, right? To get it as close to the real thing so it's as it closely represents the real thing as possible. So types of models. Models are made in different ways. One way is to build a physical model. An earthquake shake table with model buildings on it is a physical model, right? The table moves, the buildings on it do whatever they're going to do, and the scientists observe what they do. So scientists can speed up time in computer models so that they can see what might happen long in the future. Drawing diagrams and flowcharts is a third way to make models. These two-dimensional models can be used to show how ideas are related. And over here they show the image from an earthquake to go with what they said about the earthquake shake tables. So let's move on to the next part. Here's a model of the motion of real earthquakes, like we were talking about up there. Let's keep moving on. How to excel in experimentation. So you're enjoying a frozen juice pop. The heat of your tongue melts the pop. As you slurp the liquid, you think about how different substances freeze. So this lady is thinking, I know that water freezes at 0 degrees Celsius. How does adding other substances to water affect the temperature at which it freezes, right? So this is the start of her investigation. She's asking a question. So you know a freezer pop is cold enough to freeze water. You know a freezer is cold enough to freeze water. You also know that juice is mostly water. You ask, does adding substances to water affect its freezing point? Many science questions, including this one, can be answered by doing experiments. An experiment is a procedure used to test a hypothesis, so a prediction. It's a good idea to make some observations before starting a hypothesis. For example, you might put a small amount of orange juice in the freezer. Then you check it every few minutes to look for changes. So what this is doing is you're also pulling on prior information to see if what you're doing is testable and what might happen, right? So you know that her knowing that water freezes at 0 degrees Celsius is her prior knowledge and what she brings to the experiment. Hypothesize, very important. A hypothesis is a statement that can be tested and will explain what can happen in an investigation. So, in the case of the freezing question, you think about what you already know, and you can also talk to other people, and you can do research, such as asking an expert. You find out that the freezing point and melting point of a material should be the same temperature. An expert suggests that it is better to measure the melting point than the freezing point. So in this hypothesize bubble, it says any substance dissolved in water will blank the temperature. So it could, the hypothesis is filling in that blank. That's something to predict. It will blank the temperature at which the mixture freezes and melts. Okay, so what we're looking at is you are trying to figure out, will it raise? Will it lower? What will it do to the temperature? That when you add it to water, it will what will it do? That's what you're stating. It's a prediction, a statement based on what you have observed before making your hypothesis. So we're moving on to design an experiment. A well-designed experiment has 2 or more setups. This allows you to compare results among them. For the freezing melting experiment that we just talked about, each setup will be a cup of liquid. Here's the cup of liquid. So she's got different things taped to the side of the cups, and we'll go over them right now. A variable, your vocabulary word, a variable is in any condition in an experiment that can be changed. So that is the part of the experiment where the investigator is changing it. In most experiments, there are many, many variables to consider. The trick is to keep all variables the same in each setup, except one. That one variable is the one you will test. Okay, so among the setups should be one called the control. The control is the setup to which, the control is the setup to which you will compare all the others. Okay? You've decided to dissolve different substances in water and freeze them. Then you plan to take them out of the freezer and use a thermometer to check the temperature as they melt. So in this part right here, it's a very important part. It's one of the activities you do for your read along or follow along. It's identifying the control variable, identifying control variables. So when you identify and control variables, you determine which conditions should stay the same and which one should be changed. Circle the variable that will be tested. Underline based on what her original question was. Okay, so you got to keep that in mind. Underline the variables that will remain the same each time. Okay, think back. Look at the picture also here. What's going to stay the same each time? Okay, and then you can use this page and what we talked about to answer those, to circle those statements. So the only difference between these cups is what was added to the water. So we're moving on to carrying out the procedure. Carry out the procedure. A procedure is the steps you follow in your experiment. Let's say you fill each of the four identical cups with a different liquid: pure water, salt water, water with sugar, water with vinegar. Next, you put a thermometer in each cup. Then you place all 4 cups in a freezer. When all 4 are frozen, you take them out of the freezer and watch what happens. When the contents are half melted, you measure the temperatures of each liquid. The temperature is the melting point. It's a good idea to repeat your procedure several times. Each time you will have more results to consider. If the results are very similar, you will have more evidence to support your conclusions. So it's very important to do the same procedure each time you do your experiment, and to do that several times. Remember the bubble mania? We did it 3 times. We tested it 3 times, and we did it the same way each time. Record and analyze data. This is I keep saying it's very important. Each part is very important. So record and analyze the data. You could write down your observations as sentences, or you can make a table to fill it in. No matter how you do it, make sure you record correctly. Check twice or have a team member check. Once the experiment is completed and the data recorded, you can analyze your results. If your data is in the form of numbers, math skills will come in handy, as it usually does in science and math together. They are partners. For example, in the data table below, you'll need to know how to read, write, and compare decimals, because she uses decimals as her unit of measurement for her data. So draw conclusions and evaluate the hypothesis. Remember we talked about conclusions earlier. You draw conclusions based on your results. Remember that all conclusions must be supported with the evidence. The more evidence you have, the stronger your conclusion. Once you've reached a conclusion, look at your hypothesis. Decide if the hypothesis is supported or not. If not, try rethinking your hypothesis. Then design a new experiment to test it. That's what scientists do. Build on what they learn. So now we're going to move on to why it matters, special delivery and data display. Once you've completed a scientific investigation, you want more people to know about it, right, and know about your results. So what's the best way to communicate the data you collected? As part of their investigations, scientists collect, record, and interpret data, right? Look at this type of data, how it's represented. It's represented in a circle graph, right? There's more than one way to display or communicate your data. Some kinds of displays are more suited to certain kinds of data, right? So you use specific graphs to show specific pieces of scientific data. They need to be compatible. So line graphs are suited to show change, right? Either the line is going to go up, down, or it's going to be on a plateau, right? It just keeps going on a level level direction. It doesn't really go up or down. Circle graphs are suited for comparing parts of a whole. So if you want to show fractions or percentages, then you're going to use a circle graph. Diagrams are suited to show data that do not include numbers, right? This diagram shows how an orangutan uses a tool to eat seeds and fruit. So there's different ways that you can show your data. Bar graphs are suited to compare things or groups of things. When your data are in categories, you use a bar graph. Okay? And then that concludes our lesson 3. You have a sum it up after reading this and listening to this, and you have your follow along activity. I hope you guys found this really interesting, and I will be back with your lesson 5. I'll see you later on this week.